Okay, so the topic of this week's lecture is structure formation. So we'll discuss how large-scale structures arise in our universe. So initially, we've been working under certain assumptions. We've been working under the assumption that the universe is homogeneous and isotropic. So this assumption is what we use to derive the Friedmann equations and the acceleration equation and all the dynamical equations describe the evolution of the scale factor in our universe. But these assumptions are operative on large scales. By which I mean distances that are larger than 100 megaparsecs. So on smaller scales, we have density fluctuations. Some of these density fluctuations are subatomic, some of the density fluctuations are U, some of the density fluctuations are superclusters and voids in the universe. So they range from subatomic size to the size of superclusters and voids, which are about 50 megaparsecs in size. So what happens if we start relaxing the assumptions about homogeneity and isotropy? How do we describe the evolution of these structures? So we relax our assumptions, and we study the evolution of these density fluctuations. In an effort to understand how a large-scale structure in the universe arises. So, what exactly do we mean by large-scale structure? So, very complicated dynamics goes into smaller scale structures. For example, the formation of solar systems, the formation of galaxies are what we consider small scale structure. Whereas large scale structures correspond to sizes larger than individual galaxies. So groups of galaxies, for example, clusters, superclusters, and voids. The largest things we see when we survey the universe is what's described by large-scale structure. And our effort today will be trying to understand how this large-scale structure arises from a theory. Okay, so we have some data, the 2DF Galaxy Redshift Survey. And posted on the notes, I have some pictures from the Sloan Digital Sky Survey, which shows the structure of the superclusters and these voids. So what we're trying to do is construct reasonable models of the kind of pictures that you see in the sky. So the most prominent structures in these are the superclusters and the voids. The superclusters, these are depending upon the angle you view them at, they're flattened or they're elongated. So they're shaped in a roughly planar sort of way or a roughly linear sort of way. Whereas the voids, these guys are roughly spherical in shape. So a supercluster, as the name suggests, consists of a bunch of clusters. And if you were to write down your full postal address would include Virgo supercluster. The clusters themselves, these are fully collapsed objects that are in equilibrium. The meaning of equilibrium here is the virial theorem applies. The distinction between cluster and supercluster is superclusters are the process of collapsing. Under their self-gravity. So superclusters are not quite in equilibrium. So the claim is that these structures, these superclusters and voids, these arise from gravitational instabilities. So our role is to make this precise and understand what these gravitational instabilities are doing. So, roughly speaking, very early in the universe, we saw slight inhomogeneities in the CMB, and we also saw that there were quantum fluctuations during inflation that were extended by the exponential expansion of the universe during the inflationary phase. So in matter domination, so the universe is roughly 50,000 years old, when matter domination takes over, there are slightly overdense regions and slightly underdense regions. So the overdense regions, because they're overdense, these regions expand slightly slower than the average region, and they collapse and form gravitationally bound objects. These slightly dense regions then draw matter from the surrounding environment, and the surrounding underdense regions and become more and more dense. So these structures will end up growing as we continue. So the first thing we'll focus on is examining how gravitational instabilities in the static universe lead to these structures. Okay. So let's first of all study gravitational instabilities. Okay, so construct a mean energy density as a function of time. The mean energy density as a function of time is just the average over the volume of the space divided by, well, the average of the volume of the space, we divide the volume, and we take the energy density at each particular point in space, and we integrate over the space. So, in order for this to make sense, the volume we're integrating over must be sufficiently large. When we've done this average, we find some function of time that describes the mean energy density in the universe. So we're interested in how this energy density at a particular point in space, time, differs from the mean energy density. So we construct a dimensionless parameter, delta of R and T, which is the energy density at location R at time t, minus the average energy density at time t, normalized by the average energy density at time t. So this is a dimensionless density fluctuation that tells us how the local energy density is different from the mean energy density in some volume that we have. So delta then is negative in the underdense regions, where the mean energy density is smaller, and it's positive in the overdense regions. So in particular, because the energy density can at minimum be 0, the minimum value of delta is -1 when this guy is 0, we need to divide minus epsilon bar by epsilon bar to get -1, but it's unbounded from above. So what we'll do is we'll write some differential equations for delta and solve them in order to describe the origin of structure. So in particular, we're interested in how small fluctuations will behave. So we take the magnitude of delta to be much, much less than 1. Okay, so we'll start with an approximately homogeneous and isotropic universe with some small fluctuations, delta, in the mass density. So we'll consider a matter-only universe to start. And we'll have a uniform mass density rho bar. So now we'll take a small sphere of radius r, and we'll say the mass density inside the sphere is slightly different from the mean mass density. So the mass density inside the sphere will be rho bar times 1 plus delta. And again, the absolute value of delta is much, much less than 1. So we want to consider what we can say about this slightly different density in some region of space and see how that evolves. So we'll work in the Newtonian approximation. So with this approximation, the change in the second derivative, well, the second derivative of r, the acceleration, if you like, is minus g Newton times the change in the mass divided by r squared. So essentially, this is the content of Newton's second law. So we know that the delta m is related to the difference between the mass distribution within the sphere of interest and the mass distribution outside. So this is 4/3 pi r cubed, the volume of the sphere, times rho bar delta. So delta m is the volume times the density minus the mean density. Okay, so that's where this rho bar delta term here appears. So if we divide, so we have r squared in the denominator here, r cubed in the numerator there. So we divide by r, we get r double dot over r is minus 4/3 pi g Newton rho bar delta of t. So if delta is bigger than 0, meaning the region is slightly overdense, this means that because of the sign, the sphere is collapsing because of a slight excess of mass within the sphere. Now, this dynamical equation has two functions of t. We have r of t and we have delta of t. So how can we simplify this equation? We just show that these two functions are not independent. So we know that the conservation of mass applies as the sphere is contracting. The mass is 4/3 pi r of t cubed, the volume of the sphere, times the density, which is 1 plus delta of t times rho bar. And this guy is constant. So, in particular, we can write r of t by solving for the r of t, this expression here. We can write r of t as some reference r0 times 1 plus delta of t to the minus 1/3. So this r0 is 3 times the mass divided by 4 pi rho bar to the 1/3. And this guy is constant. So we parameterized r in terms of delta now. So then we can plug back in to the expression we had previously. So, in particular, if we're working in the approximation that delta is small, then Taylor's theorem tells us that r of t is approximately r0 times 1 minus 1/3 delta of t. So in particular, the second derivative, r double dot of t, is approximately r0, 1 minus 1/3 delta double dot of t. Sorry, this is, there's no 1 here. It's minus 1/3 delta double dot of t. So this is then the same as approximately minus 1/3 r delta double dot of t, working leading order in delta. So we're dropping all terms in which delta squared appears. So plugging this result back into this equation here, we find that r double dot over r is minus 1/3 delta double dot of t, which is equal to minus 4/3 pi g Newton rho bar delta of t. So, simplifying this, delta double dot of t is 4 pi g Newton rho bar delta of t. So if delta double dot is proportional to delta, we know what the answer is. Delta of t is a1 exponential t over some dynamical scale, t dynamical, plus a2 exponential minus t over t dynamical. And t dynamical here is 1 over 4 pi g Newton rho bar, the 1/2, or if we prefer, c squared over 4 pi g Newton epsilon bar to the 1/2. Just changing from description in terms of rho bar to description in terms of epsilon bar. The coefficients which appear in the expression for delta, a1 and a2, these are set by initial conditions or boundary conditions in solving the differential equation. So suppose we have some overdense sphere which starts out at rest. Let's see what we can say about how it evolved. So if we start off at rest, this means at t equals 0, delta dot equals 0. So delta dot is a1 over t dynamical exponential t over t dynamical minus a2 over t dynamical exponential minus t over t dynamical. So at t equals 0, these exponentials give us 1. So this tells us that delta dot equals 0, that a1 equals a2, and moreover, these guys are delta of 0 over 2, since we have the initial condition that delta at t equals 0 is delta 0. Okay, so after a few dynamical timescales, the exponential, which is proportional to a2, the one with the minus sign in it, that dies off. Because after several dynamical timescales, even the minus some large number is a very small number. So all that really remains at the end is a term proportional to a1. So after several dynamical scales, we just have delta of t is a1 exponential t over t dynamic. So what the conclusion we draw from this is that gravity makes small fluctuations grow exponentially with time. So this pertains to a static pressureless medium So we'll see what happens when we relax these assumptions, because of course we're not working in a static medium, we're working in an expanding universe. Okay? So we've seen, however, that we can characterize the behavior of density fluctuations in some medium, and we've seen that in certain circumstances, these density fluctuations can grow exponentially with time. And these fluctuations then lead to large-scale structures arising in the universe. So we're going to characterize exactly when this happens. So we'll define a parameter called the Jeans length. So this is named after some dude named Jeans. It's not related to any clothing you may or may not be wearing. The density of air in the room, rho bar, is approximately 1 kilogram per meter cubed. So the dynamical time scale associated to this density is about 9 hours. So based on our discussion, we can ask a very naive question: what keeps small density fluctuations in the air from expanding exponentially? So why should we not be worried about breathing in this room 9 hours later? Well, what keeps these small density fluctuations from growing exponentially is the pressure. Whereas before, we were working in a universe that was essentially pressureless. So W equals 0, corresponding to matter domination in the universe that we described previously. So for a non-relativistic gas, we have the equation of state parameter W, which is about kBt over mu c squared, where mu is the mean mass per particle in our fluid. Now, we were able to approximate this as 0 because for the non-relativistic gas, this is in fact a very tiny number, but it's not quite 0 in truth. So suppose we have a sphere of gas that's compressed by gravity. So as the sphere of gas is compressed by gravity, a pressure gradient develops. And eventually, you achieve hydrostatic equilibrium. So for example, star, our sun, is sustained a radiation pressure which balances the inward collapse of gravity. So in hydrostatic equilibrium, gravity and pressure exactly balance. So the condition of hydrostatic equilibrium is not generically attained by substances in the universe. So suppose we return to our overdense sphere with initial radius r, we want to ask under what conditions will this achieve equilibrium and when will it not achieve equilibrium. So, given that there is this dynamical scale, T din, which is proportional to c squared over g Newton epsilon bar the 1/2, we want to consider some attempted collapse and have this be countered by some pressure gradient, and see when the pressure gradient with this perturbation prevents the collapse from happening. So the problem with this kind of thing happening is that ultimately the steepening of the pressure gradient only travels at the speed of sound. So sound is in fact some pressure wave, as we know. So the pressure gradient travels at the speed of sound, and as a result, the time associated to the pressure is like this distance scale r divided by the speed of sound. That's the only way you get something with units of time. We want to compare this time associated to the pressure gradient to the time associated to the dynamical collapse. Okay. So remember from earlier on in the course, the speed of sound, cs, is c times the rate of change of pressure with respect to the energy density. So the equation of state is P equals W epsilon, dP d epsilon is W, factor of a half there. So this is equal to square root W times the speed of light. So CS is a local sound speed in our medium. So this fixes the time scale associated to how the pressure gradient moves. And again, when I compare this to the time scale associated to the dynamical collapse of stuff in our universe. Okay, so hydrostatic equilibrium requires the time scale associated to pressure be less than the time scale associated to dynamical collapse. So in particular, we can write down some length scale associated to these time scales. So lambda j, the gene's length, is the speed of sound times this upper bound, T dynamical. So this is CS, c squared over d Newton epsilon bar to the half. And CS times T pressure, well, T pressure was just defined as R divided by CS. So this is just R. And if this is less than CS times T dynamical, which is the gene's length, then we have interesting things happening. So over dense regions, larger than the gene's length, these guys collapse due to gravity. And over dense regions smaller than Jeans length, these oscillate in density. So, in other words, in these regions, there's stable sound waves that propagate. So, in our case, in the scenario of the air in the room that we talked about to begin with, the associated Jeans length is about 10 to the 5 kilometers, which is much, much larger than the height of the atmosphere. So as a result, density fluctuations in the air, these won't collapse. Okay, so let's think about a spatially flat universe again. So a more precise calculation here, by the way, is 2 pi speed of sound times t dynamical. So if you get the factors right, you should find this factor 2 pi up front. Okay, so let's consider a spatially flat universe. In this spatially flat universe, let's take delta, the fluctuation, to be small, and let's see the various competing features of our setup. So, in addition to t dynamical, there's one other natural scale in the problem. This natural scale is h inverse, which is 3c squared over 8 pi g Newton epsilon bar to the half, which is square root 3 over 2 t dynamical, using the definition for t dynamical that we gave earlier. So this is about 1.22 times t dynamical. So lambda Jeans, the Jeans length, is 2 pi speed of sound times t dynamical, which is 2 pi times 2/3 the 1/2 square root w c over h. And in radiation nomination, W is 1/3, so this is equal to speed of sound, CS, is c over root 3, which is 0.58 times c. So in this one component universe that's radiation dominated, we have lambda Jeans is 2 pi root 2 over 3 c over h, which is about 3.0 c over h. So this means that density fluctuations are pressure supported if they're smaller than about 3 times the Hubble distance. So radiation domination universe can have density fluctuations smaller than lambda genes, which is about 3 times the Hubble distance, that give stable sound waves and they don't collapse under their own gravity. Now, let's see what happens to a different kind of universe, one in which we have square root w being much, much less than 1. So this is like matter domination. So a non-relativistic component of the universe with a very, very small equation of state parameter. Initially, this is a bit complicated because the baryonic component for which this equation holds, this was coupled to the photons. So remember that before the surface of glass scattering was crossed, the photons were strongly interacting with the matter. So before decoupling happened, you couldn't think about the baryons and photons separately. There was a single baryon-photon fluid. So until Z decoupling, which is about Z last scattering, which is about 1100, we had a single baryon-photon fluid. And the Hubble distance, C over H evaluated Z decoupling, was about 0.2 megaparsecs distributed. And at decoupling, we have various densities for stuff. The energy density of baryons was about 2.8 times 10 to the 11 MeV per meter cubed, meaning the mass density in the baryons was about 5.0 times 10 to the minus 19 kilograms per meter cubed. And the energy density in the photons was 3.8 times 10 to the 11 MeV per meter cubed, which is about 1.4 times the energy density in the baryons. So you want to examine what happens to the photon-baryon fluid before decoupling, and what happens to the separate fluids, the photons and the baryons, after decoupling. So before decoupling, they had a single photon baryon fluid with the energy density of the photons larger than the energy density in the baryons. So suppose we think about the baryons as some minor contaminant in the photon with respect to the photons. So lambda genes before decoupling was 3c over h evaluated as decoupling. So this is about 0.6 megaparsecs, which is about 1.9 times 10 to the 22 meters. So the baryonic Jeans mass which we'll call mj, is baryonic density times 4/3 pi lambda Jeans cubed. And this works out to be about 7 times 10 to the 18 solar masses, which is larger than the baryonic mass of even the largest supercluster that we see. Okay, so let's contrast this to what happens after decoupling. So after decoupling, the mean free path of the photons is essentially infinite. So the photons and the baryons no longer interact. And the sound speed in a medium comprised of photons is c over root 3, which was 0.58 c. And the sound speed in the medium of baryons is kBt over mu c squared to the 1/2 times c. So at decoupling, Boltzmann T decoupling was about 0.26 electron volts. Mc squared, mu c squared was about 1.22. MP c squared, which is about 1140 MeV. This is 1.22 there in order to account for the helium fraction Yp of about 0.24. And we find that the sound speed in baryons, then, plugging these values in, is about 1.5 times 10 to the minus 5 times c. So the ratio F, Cs in the baryons to Cs in the photons, this is about 2.6 times 10 to the minus 5. So in particular, the Jeans length after decoupling compared to the Jeans length before decoupling is down by a factor of F cubed. So this works out to about 1 times 10 to the 5th solar masses, which is the baryonic mass of a dwarf galaxy. So by comparison, the Milky Way is about 10 to the 11 solar masses. Okay, so we've done some calculations. What's the physical meaning of this? How do we interpret this? So the interpretation is that there are perturbations in the baryon density and these are from supercluster scales two dwarf galaxy scales. So these perturbations, because the baryonic James mass was so large, these perturbations couldn't grow in their amplitude until decoupling happened. So the time for decoupling was about 380,000 years. This corresponds to the age of the cosmic microwave background, roughly speaking. After decoupling, we have a growth of these density perturbations. And as the universe continued to expand, it also cooled. And as a result, the baryonic James mass dropped still further. Okay, so far, we've mostly discussed instabilities in terms of the static universe, whereas we know that the universe is expanding, and we'd like to revisit the story in the context of the expanding universe. So that's the next thing we'll do. Okay, so we'll consider instabilities now in an expanding universe. Okay, so essentially, density perturbations they're smaller than the Hubble distance. These grow in their amplitude. When they're no longer pressure supported. So for baryonic matter, This happens at decoupling. For dark matter, this happens as the thermal energy of our dark matter particles drops below their rest energy. So we've noticed there was CMB. We've also argued previously there's a cosmic neutrino background, and 1 plus z is A inverse, which is about m nu c squared over 5 times 10 to the minus 4 electron volts, where m nu is the mass of the neutrino, and these are neutrinos before they become non-relativistic. Similarly to the cosmic neutrino background, we'll have a cosmic WIMP background if dark matter consists of weakly interacting massive particles. And here, m WIMP c squared is much, much bigger than 2 electron volts. These become non-relativistic. Much earlier. These become non-relativistic around, well, before radiation matter quality, which happened around 3570 redshift. So now we want to consider how all this behavior manifests in an expanding universe. So before, in doing much of this analysis, we had the fluctuation proportional to the exponential of T over T dynamical. In an expanding universe, we have competing effects. So in an expanding universe, T dynamical was like C over G Newton, epsilon bar to 1/2, C squared. But H inverse here is also C squared G Newton, epsilon bar to the 1/2. So the competing effects are that soft gravity makes overdense regions become more dense. As gravitational collapse happens, the region in space becomes denser. But expansion makes the overdense regions less dense. So there's a competition between the effects of gravitational collapse and the effect of the expansion of the universe. So let's return to our Newtonian approximation. Let's consider pressureless matter. With rho of t as rho bar of t, 1 plus delta of t, and again we'll work with the absolute value of delta much less than 1. So the Newtonian approximation, R double dot, was minus g Newton m over r squared. So this was minus g Newton over r squared, 4/3 pi r cubed times rho, or equivalently, r double dot over r was minus 4 pi g Newton over 3 rho bar 1 plus delta. Okay, so we also had the relation that the mass was 4/3 pi rho bar 1 plus delta r cubed, and this was a constant. Okay, so let's see how different things behave. Okay, so looking at the expression for mass, we see that R is proportional to rho bar to the minus 1/3 times 1 plus delta to the minus 1/3. So essentially, R is proportional to the density to the minus 1/3 power. But we know that rho bar of t, that's proportional to 1 over the scale factor cubed. This is because the density is diluting with the volume. And the volume is set by the cube of the scale factor. So, R is proportional to A, scale factor, times 1 plus delta to the minus 1/3. Okay, so what this means is that if the sphere is slightly overdense, its radius will grow slightly less rapidly than the scale factor, because this term, 1 plus delta to the minus 1/3, that appears in this expression. Okay, so let's take two derivatives of R. So R dot will scale like A dot over A, 1 plus delta to the minus 1/3. Sorry, just A dot. So A dot over A here. 1 plus delta to the minus 1/3. Plus A minus 1/3, 1 plus delta to the the minus 4/3 delta dot. Okay, so now dividing both sides by r dot over r scales like a dot over a. 1 plus deltas will cancel. Minus, we're dividing by a 1 plus delta to the minus 1/3. The a will cancel in the second term. 1 plus delta to the minus 1 power. And there's a delta dot. Okay, so that's the first derivative. The second derivative, so, okay, we'll just continue. The second derivative, r double dot over r minus r dot over r squared. That's just hitting d by dt on the left-hand side. On the right-hand side, we have a double dot over a minus a dot over a squared plus 2/3 a dot over a 1 plus delta inverse delta dot. That's the cross term. And then the final term is minus 1/9, 1 plus delta to the minus 2, delta dot squared, minus 1/3, 1 plus delta inverse, delta double dot. Okay, so we've assumed that delta is much less than 1. So I'll drop all terms that are quadratic in delta. So in particular, we have, okay, so this left-hand side is r dot over r. We just square this expression here. So this is minus a dot over a squared plus 2/3 a dot over a 1 plus delta inverse delta dot minus 1/9. What did I do wrong? Minus 1/9. 1 plus delta to the minus 2 delta dot squared. So here I did something wrong. Differentiating this guy here. The first term is indeed a double dot over a. Next term is minus a dot over a squared. Then I've got minus 2/3 1 plus delta to the minus 2 delta dot squared minus 1/3 1 plus delta inverse delta dot. Okay, so this term here will cancel that term there. Then we have r double dot over r equals a double dot over a. So these terms, this term canceled. This term survived. Then we have, at leading order, minus 1/3 delta double dot minus, Okay, so this term is delta dot squared. So we're just going to ignore this term, it's small. Then we have this term here, minus 2/3, bring it to the opposite side. A dot over A, delta dot. And then we have, this term is delta dot squared, so it's going to cancel by virtue of the smallness of delta. And this is the expression we have at the end. R double dot over R is A double dot over A, minus 1/3 delta double dot, minus 2/3 A dot over A times delta dot. So you've dropped terms of order delta squared. The problem with doing algebra on the board is that one makes errors. But I believe that's the correct expression at the end. Okay, so we found an equation that says R double dot over R is A double dot over A minus 2/3 A dot over A, delta dot, minus 1/3 delta double dot, dropping order delta squared terms. Okay, so we had a previous expression for all R double dot over R, which we just erased. That previous expression told us that this was minus 4/3 pi g Newton rho bar to the 1 plus delta. So in the case where delta equals 0, there's no fluctuation. This is A double dot over A is minus 4/3 pi g Newton rho bar, as this term will vanish and that term will vanish. And this guy also vanishes. So this is just the acceleration equation for a homogeneous isotopic universe that's pressureless. So that's correct. If we have, so let's subtract this result from the previous equation. So in this case, we find that minus 1/3 delta double dot minus 2/3 A dot over A delta dot is minus 4/3 pi g Newton rho bar delta, or multiplying everything by minus 3, delta double dot plus twice the Hubble parameter delta dot minus 4 pi g Newton rho bar delta equals 0. Okay, so if we have a static universe, H is 0, since A dot is 0 for a static universe, and we get delta double dot is equal to 4 pi g Newton rho bar delta, which is what we had previously. So this new term we introduced here, the term proportional to the Hubble parameter, the H delta dot term, is called the Hubble friction term. So if we write this as delta double dot plus 2H delta dot is minus 4 pi g Newton delta, this looks, roughly speaking, like an exponential with some friction dampening term. And that's what we have here. This Hubble friction term, it slows the growth of perturbations in an expanding universe. Okay, so that's our naive Newtonian calculation. We can upgrade this to a general relativity calculation. I'll just quote the result when we do this. So upgrading this to a fully relativistic calculation, we'll express things in terms of epsilon bar instead of rho bar. And we find that delta double dot plus 2h delta dot is 4 pi g Newton over c squared epsilon m bar delta. So this equation, this applies to a universe with radiation or cosmological constant just as well as it applies to a universe with matter. It applies to a multi-component universe. The important thing to keep in mind, however, is that delta is the fluctuation only in the energy density of the matter. Okay? So whereas the energy density can correspond to other things, delta corresponds only to matter. And in fact, omega m is epsilon m bar over epsilon c, which is 8 pi g Newton over 3 c squared h squared epsilon m bar. So you can write this expression as delta double dot plus 2h delta dot minus 3 halves omega m h squared delta equals 0. So all the radiation dynamics and the dynamics of cosmological constant or multi-component universe, etc., is in the Hubble parameter. Omega m is just a function of the energy density in the matter, and delta is the fluctuation in the energy density in the matter compared to the mean energy density in the matter. So suppose you're looking at radiation domination. In radiation domination, we have omega m being much, much less than 1. And in radiation domination, we know that h is 1 over 2t. So this equation here is approximately delta double dot plus 1 over t delta dot is 0. So solution to this equation, delta t, is a constant plus a logarithm in time. So what this says is the density fluctuations in, say, dark matter, these will grow logarithmically in the radiation-dominated epoch. If we had, instead of radiation domination, we had cosmological constant domination, we know that, again, omega matter is very small. the equation here is delta double dot plus 2h lambda, which is constant, delta dot is approximately 0. So delta of t here is some constant plus c2 e to the minus 2h delta t. So fluctuations in the matter reach a constant amplitude, and the average matter density, epsilon matter bar, this falls with the expanding universe. And in cosmological constant domination, the universe is expanding exponentially. So the interesting case is not radiation domination or cosmological constant domination. The interesting case is matter domination, where we have some equation which is non-trivial to look at with some interesting dynamics. Okay, suppose we have matter domination. Omega matter, we'll say it's 1. H is 2 over 3t. So delta double dot plus 4 over 3t delta dot minus 2 over 3 t squared delta is equal to 0. The ansatz we make is a power law ansatz. We'll say delta is equal to some constant d times t to the n. So this equation then becomes n times n minus 1 d t to the n minus 2 plus 4 over 3t n d t to the n minus 1 minus 2 over 3 t squared d t to the n equals 0. By dimensional analysis, we see that each term is proportional to t to the n minus 2. So the equation for n is that n times n minus 1 plus 4/3 n minus 2/3 equals 0, which implies that n equals either minus 1 or 2/3. So delta of t is d1 t to the 2/3 plus d2 t inverse. This term is proportional to an inverse power of time. So this guy is negligible rate times. And we have power law growth of fluctuations. So delta is proportional to t to the 2/3. Which is proportional to the scale factor a of t, which is proportional to 1 over 1 plus c. Okay, so this analysis applies assuming the scale factor is much, much less than 1. We can't rely on this assumption when the fluctuations get large. So let's say a few words about the nonlinear regime. So when an overdense region has delta approximately 1, we can't use linear perturbation theory. The best thing to do is to put things on a computer and model this with these simulations. So when we do this, we find is that when delta is about 1, we break away from the Hubble flow. And something collapses within 1 or 2 oscillations. After which, we have equilibrium. Meaning the virial theorem applies. And we have a gravitationally bound structure. The baryonic matter then cools. It radiates energy. And it falls to the center. And eventually forms stars. Meanwhile, the non-baryonic stuff, the dark matter, it forms a halo. So it's a model for galaxy formation in which we have a baryonic center which radiates and shines, surrounded by the spherical halo. So a picture is when you look at the density fluctuations with respect to time, for these oscillations. Dark matter behaves like so. And the baryons with dark matter, so baryons without dark matter behave like this. Baryons with dark matter follow this curve. And essentially, the fact that there is dark matter means that the structure formation happens much earlier. Okay. So, in effect, these acoustic oscillations start to describe how structures like galaxies form. So, this is most of what I want to say about structure formation. There's one last thing that I'd like to discuss, which is the power spectrum. Okay, so the equation we derived, or motivated, delta double dot plus 2h delta dot is 4 pi g Newton over c squared epsilon m bar delta. This applies to low amplitude perturbations of any shape. Okay? So in particular, spherical symmetry is not necessary for this analysis. What we're going to do is we're going to use current large-scale structure lets us deduce the low amplitude density fluctuations at early times. Okay, so remember that we're working in an FRW universe. The FRW universe has a metric which is dependent on the scale factor and the curvature. And we define the proper distance is some time as the scale factor times r. So r is the co-moving distance. dp of ti is the proper distance. And r is r, theta, and phi. We'll take it to be nearly constant if delta is small. And we try to analyze certain aspects of behavior, just like we analyze aspects of behavior for the CMB. As for the CMB, we're not particularly interested in what happens in a particular direction. We're sort of interested in the average behavior. So what we'll do here is we'll take delta of r to be v over 2 pi cubed integral over a momentum space e to the minus I k dot r delta k. Or equivalently, the modes delta k are 1 over v integral d3r e to the I k dot r delta of r. So essentially this defines the Fourier transform and the inverse Fourier transform. We break our function into essentially sine waves with some wave number k, and the co-moving wavelength is 2 pi over k. We can think about these delta k's as being some magnitude delta k with some phase e to the I phi k associated to it. And it turns out that each of these modes, each of these delta k's, they obey the fluctuation equation we derived. So that for delta k much less than 1, delta k double dot plus 2h delta k dot minus 3 halves omega m h squared delta k equals 0. So even after fluctuations with some short wavelength have reached delta k about 1 and collapse, this equation still applies to the longer wavelengths, since we're treating each of these delta k's as, for the most part, independent Fourier node of delta of r. So we can study large-scale structure after smaller structures have formed. So for example, these short wavelengths collapsing may create galaxies and clusters, but the dynamic superclusters discovered by the longer wavelengths. We can still study this using this Fourier decomposition. We want to consider an object called power spectrum. P of k is the mean value of delta k squared, where we average over all possible orientations of k. And if the phases phi k are uncorrelated, then delta of r is called a Gaussian field. And if a Gaussian field is homogeneous and isotropic, then all statistical features are in the power spectrum P of k. In fact, we have P of delta is 1 over root 2 pi sigma e exponential minus delta squared over 2r squared, and hence Gaussian. Sigma here is v over 2 pi cubed integral d3k p of k, which is v over 2 pi squared integral 0 to infinity dk a squared p of k. So most inflationary models predict near Gaussian behavior. And one way to characterize the difference between various inflationary scenarios is to look for non-Gaussianity and characterize non-Gaussianity in the system. In fact, it turns out that P of k is, in general, some power law k to the n, and the case n equals 1 is called a Harrison-Zeldovich spectrum. Okay, so let's say a few words about why the Harrison-Zeldovich spectrum is interesting, and then we'll stop there. Okay, so the average mass is 4/3 pi L cubed epsilon m0 divided by c squared. So epsilon m0 divided by c squared gives us rho m0, and L is a co-moving radius. So fluctuations in the mass, m minus the average mass divided by the average mass squared, this average value is proportional to k cubed times the power spectrum p of k. Now k is the wave number as 2 pi over L. So we'll define delta m over m as m minus the average mass divided by the average mass. This guy squared to the 1/2. And this is proportional. You plug things in to, if you plug things into here, and you take a power spectrum that's power law, P of k goes like k to the n. This tells us this is proportional to L minus 3 plus n divided by 2. So mass is proportional to L cubed. In other words, m to the third is proportional to L. So delta m over m is proportional to m to minus 3 plus n divided by 6. Now, if n is less than minus 1/3, mass fluctuations will diverge on all scales. If n equals 1, namely the Harrison-Zildovich spectrum, delta m over m is proportional to m to the minus 2/3, which implies delta m is proportional to m to the 1/3. Now, fluctuations in gravitational potential, these scale like g Newton delta m over L, which is proportional to delta m over m to the 1/3, since L scales like m to the 1/3. So this, with the Harrison-Zildovich spectrum, since delta m also scales like m to the 1/3, this is constant. So the Harrison-Zildovich spectrum prevents the divergence of the potential on all scales. So that's why it's interesting. And in the data, we tend to see a minimal divergence from the Harrison-Zildovich spectrum. So the challenges of inflation are to come up with some model that develops, all of these structures that facilitates, this kind of behavior at late times. In particular, if we characterize the non-Gaussian features, the cosmic microwave background, then we have some handle on what the model of inflation we should be looking at is, and we have some further handle on how these fluctuations grew at late times. So right now, one of the main goals of these experiments in cosmology is to either find evidence of non-Gaussianity, to begin to characterize behavior, or to develop models that are consistent with features of the sky and features of large-scale structure that we see. So in effect, this is sort of the state of the art in cosmology right now. It's figuring out the shape of the power spectrum and using the power spectrum to characterize the behavior of the early universe. So I think that's all I want to say about structure formation. So I'll stop there, and I guess next time we'll pick up with some large-scale summary of this course.